It has been reported that the probability that an individual will develop schizophrenia over their lifetime is 0.004. In a random sample of 3,000 individuals, it was determined that 17 developed schizophrenia. Is there evidence to support the claim that the true proportion of people who will develop schizophrenia is different from 0.004 at the alpha equals 0.5 level of significance? So let's start off by writing our hypotheses. So our null hypothesis, so we have H sub 0, colon, and we're looking at the proportion, so P equals 0.004, and then our alternative is H sub 1, colon, P, and then we have different, so not equal to 0.004, and then we have an x value of 17 and our n is 3,000. So p hat, our sample proportion, is x over n, so 17 over 3,000. So we'll get an estimate on that. So 17 divided by 3,000 is approximately 0.006. So we want to perform our hypothesis test, so we want to check some conditions here to make sure that we have a normal distribution. So we're looking at a sampling distribution, so we want to have a simple random sample. So it says a random sample, so we're good to go in that condition, and that we have our sample size is less than or equal to 0.05 of the population size. And so I would assume if we're talking about 3,000 individuals that is less there. So if we look at 3,000 divided by 0.05, then that would be 60,000 would have to be our population size there, and we're looking at that, so we're good to go there. So that's either our condition, or we can say that we're looking at that the sampled values are independent. So we're good to go in that condition. And then our last, check mark here, and our last condition here is that n times p naught times 1 minus p naught is greater than or equal to 10. So this is 3,000 times 0.004 times the quantity 1 minus 0.004. So let's type that in our calculator. So 3,000, open parenthesis, 0.004, close parenthesis, open parenthesis, 1 minus 0.004, close parenthesis, enter, and we get 11.952. So that is greater than 10. So we have a normal distribution there, and then we can use that to find our test statistic, and then find our p-value that we're looking at. So we want to find our test statistic, so we'll do that by hand, and then we will use StatCrunch to find that. So we're looking at the sampling distribution of p hat. So our mean here is p, or p naught, and then our standard deviation here, this is what we're looking at here, as our standard deviation. So we're looking at the sampling distribution of p hat. So this is the square root of 0.004 times 1 minus 0.004, all divided by 3,000. right? And so we want to find our test statistic. And so our test statistic here is marked as C sub 0. And this is going to be P hat minus P sub 0, which is our mean, over our standard deviation. So this is 17 out of 3,000 minus 0.004 divided by the square root of 0.004 times 1 minus 0.004 divided by 3,000. So let's type that in our calculator to get our test statistic. So we're going to be careful here with the parentheses. So parentheses, two open parentheses here. And then we're going to close it there to close off our fraction, minus 0.004, close parenthesis for our numerator, divided by the square root, so second x squared. Open parenthesis for the numerator, 0.004, open parenthesis, 1 minus 0.004, close parenthesis to close off our numerator, divided by 3,000. And close that for the square root. So this is approximately 1.45. Double check the rounding there. So that's our test statistic. So the value that corresponds to our p hat here, if we were to kind of look at this as a normal distribution. So what we're looking at here, so we want to compare this to our critical values to do the classical approach. And so our critical values, we just have two since we're dealing with different. We want to look at alpha is 0.05. And we are dealing with a two-tailed test, so what we can do is pull up our table here, and we have 0.05 and two-tailed, so our critical values are plus and minus 1.96. So we have our critical region here. This is negative 1.96, so the critical value, and positive 1.96. And then we have our test statistic here as 1.45. That's going to fall here. And so we would do not reject the null hypothesis since the test statistic does not fall in the critical region. And we'll write a conclusion in a minute. So we're going to go through the p-value approach as well. So let's look at the p-value. So let's do this by hand, and then we'll by hand using StatCrunch, and then we'll go through it using StatCrunch to find the p-value and the test statistic. And so what we're looking at here is the probability that we get test statistic as extreme or more extreme. And so since we're looking at a two-tailed test, we're looking at it on either side. So this probability that z is greater than 1.45. Right. So we're going to use StatCrunch to find that. So stat calculator's normal. And so we want z is greater than 1.45. Right, so we get our value there. Pull up our calculator, and since we know that it's the metric, I can multiply that by 2. Right, so it's string or string. We also look at it on the other side. So I can multiply that value by 2 to get the p-value. So this is approximately equal to 0.1471 here. Alright, so this is approximately our p-value. So let's use StatCrunch to actually go through this. And so we're going to go to Stat, Proportion Stats, one sample with summary, and we're going to type in our number of successes, the number of observations, and then we want a hypothesis test, and our p is equal to 0.004, and our null hypothesis, and our alternative is that is not equal to 0.004, and we're going to put the p-value plot and hit compute. So we see here that our test statistic is 1.45 and our p-value is 0.1481. And if we go to our p-value plot, you will see that there's 2 portions to this, right, which is what we have here. And then so here we are so again, we want to compare the p-value to alpha. So the p-value and alpha. So our p-value is greater than alpha, we don't reject the null hypothesis. So we do not reject the null hypothesis since the p-value is greater than alpha. Therefore, there is insufficient evidence to conclude. We always conclude our alternative hypothesis. So in this case, the true proportion, we don't always conclude our alternative hypothesis, but that either there's sufficient evidence to conclude it, or sufficient or insufficient evidence to conclude the alternative. So the true proportion of people who will develop schizophrenia is different from 0.004. At the 0.05 level of significance. And so the reason that we're getting a p-value that's slightly different from the one that we're getting in StatCrunch is because we're rounding our test statistic. Right? So if we use more values of our test statistic, then we would get a more accurate result there.